Okay, hello everybody. Welcome to our first video of Chapter 2, where we discuss the derivative, what that means, and the tangent line problem. Fun stuff. So, we are going to talk about how to find the slope of a tangent line to a curve at a point. We have already discussed this. We're going to sort of review that and come up with a new strategy. We're going to use the limit definition to find the derivative of a function, and then we're going to understand the relationship between differentiability and continuity, because they are not always the same thing. Alright. So, to begin, let's discuss the tangent line problem. The tangent line problem. Now, this is review. We did talk about this in Chapter 1.1, where we know when we're given a graph, let's say of a straight line, and we have 2 points on that line. We could call the first point C, comma, f of c, and we could call the second point c plus the change in x, comma, the function of c plus the change in x. And here's what we're illustrating. We're calling, let's draw some dashed lines. We are calling the change from the point to the point, the horizontal change, we call that the change in x, or delta x, or our c plus the change in x minus c, right? The c plus change in x minus our original c. These two are equivalent statements. We call our change in y something sort of similar, right? We use the same sort of information here. The change in y is this value, f of c plus the change in x, minus this y value, f of c. And what we get to do with these two pieces of information is we get to substitute them into the slope formula that we already know. We remember from Algebra 1 that the slope formula is simply the change in y over the change in x. But if we substitute in change in y and instead we write this, let me write it right here, f of c plus change in x minus f of c. And then instead of writing change of x, we write this statement, c plus change in x minus c. We're getting closer to a different way to think about slope. And what we can do here is simplify. So we still have f of c plus change in x minus f of c all over, and you'll notice a c minus a c would cancel each other out, and we get all over change in x. And what we're going to define this as is the slope formula, or the rate of change. So let's label this rate of change. Alright, that's good to know. Now remember, when we are discussing data that is not linear, when we are discussing curves, for example, so what if we had a graph that did something like this? It curved up. No longer is it good enough for us to simply take the average rate of change. We're really not interested in that. We're not interested in the average slope from a point to a point. What we want to know now is the slope at exactly one place. And what we can do is we can call this point P, and we can call this the point C, comma, f of c. And remember, when we are finding the tangent line, what we're finding then is the slope through that point. So the reason that we make tangent lines at all is because this nice straight line through that point has the same slope as that point. That's why the tangent line is so central to us. And remember though, when we look at our rate of change formula, and we look at one single point P, we do not have a change in x. So if we wanted to find the slope of a single point, right, finding slope at a single point, and I'm going to say aka no change in x, then here's what we would have for our slope formula. We'd have f of c plus 0 minus f of c all over 0. And we can see very clearly before we do anything else that this would become undefined, and this is not something that would be useful to us. So instead, this is where those secant lines come in handy. We just make some bullet points for our thoughts here. This is where we use secant lines to approach slope of the tangent line. And again, we did an example of this in chapter 1 where we made a bunch of secant lines, correct? Here's our tangent line, a thing we want to get close to, and we started making points using P and other points on the line. So let's just start making these in blue. And I gotta pause and just say how gosh darn excited I am about this new document camera. Look at how vibrant this blue is. Look at it. It's wonderful. I'm so excited about this thing. I hope you guys are too. That's not a very accurate secant line. You get the point that I'm trying to make, though. We make these points smaller and smaller and closer to the point P. And we get slopes that are closer and closer and closer to our line. Like they kind of start out here, right? And they get closer and closer and closer to being exactly the same slope as our line through point P. That's why secant lines are helpful. And now you guys know so much about limits that we understand what we're doing with those secant lines is just finding the limit, right? We're making a bunch of secant lines. We're getting super, super close to the slope. And so what we're doing is we're finding the limit of the slope. And that is why we can define the tangent line with a slope of m as this. The limit as x approaches, oh, hang on. Let me double check because I may have forgotten to add a triangle in there. Hang on. Here I was on such a roll. 1 minute. Alrighty, so I totally forgot to add a triangle. That's what we're interested in. Okay. Got it. So we're finding the limit as the change in x approaches 0 for the change in y over the change in x, or for that rate of change function. So we're going to use f of c plus the change in x minus f of c over the change in x equals our slope, our m. So here's what we get to say. We get to use this formula to help us find slopes of nonlinear functions. How cool. If we look at linear functions, these aren't as interesting because the slope of linear functions, of linear data, is constant, doesn't change. So your strategy, whenever you're asked to find the slope at a certain point of linear functions, well, just solve for y and determine your m. Determine the m from your slope-intercept form. Here's what I mean. If we're asked find the slope of the graph when c equals 2, and we are given the function of f of x is 2x minus 3. Well, check it out. This is already in slope-intercept form. I have my m, which is 2. So, given this is a linear function, the slope of f of x equals, the slope of f of x is, 2, when c equals 2 or any other number. When any x value is substituted in, our slope will always be 2. Okay, moving on. Let's talk about tangent lines. This is a long title. To the graph of a non-linear function. Okay, now we're getting more interesting. So, here is our example. Find the slopes of the tangent lines to the graph f of x equals x squared plus 1 at the points 0, 1, and -1, 2. Oh boy, alright. That was a lot. Here's what we're going to do. We are going to use the properties of composite functions. We're going to use the properties of substitution to find a derivative. And here's how we're going to do that. We're going to take the function for rate of change for the slope of a tangent line, the limit as change in x approaches 0 for f of c plus change in x minus f of c all over change in x. And what we are going to do is we're going to take this f of x and we're going to use that to substitute in here. So we're going to say the limit as change of x approaches 0, and then we are going to say that this piece, the c plus the change of x, is our x, so we're going to substitute that in for x, and we're going to make that part squared, and then we're going to add 1. And here's what that looks like. Use some brackets. We're going to have our new x value, c plus change in x. We're going to square it, and we're going to say plus 1. And then we're also going to say minus our f of c, which in this case would be substituting in the c for our x value. So we're going to take c squared plus 1. And then we still have all over our change in x. Now we can start to use some algebra to help us with this. When we simplify c plus change in x squared, we're going to recall an identity. A plus b squared is equal to a squared plus 2ab plus c squared. Oh, pardon me, b squared plus b squared. And that is on your little polynomial cheat sheet, so make sure you take a look at that. Now we're going to rewrite c plus change in x squared using this. So we're going to make it c squared plus 2c times change in x plus change in x squared And then we still had plus 1, so we write that over here. And now we're going to distribute that negative, so we're going to say minus c squared minus 1. And then we still have all over change in x. Now we get to do some pretty cool stuff. We get to start canceling out things. We have a positive 1 and a negative 1. We have a negative c squared and a positive c squared. And that is all we get to cancel out for now. Let's rewrite everything else. What we have is 2c times change in x plus change in x squared all over change in x. And what we can do is separate this into two fractions, right? If we have two things over the same denominator, we can safely say that's the same as 2c times change in x all over change in x plus change in x squared over change in x. Here our change in x's would cancel. We would get 2c plus change in x, because the one change in x would go away. And now, again, we still had that limit direction the whole time. We're still trying to find the limit as change in x approaches 0. Now we can actually directly substitute in 0. So if we did that, we would get just 2c by itself. So we're going to use this 2c now to substitute in our points that we're interested in. Let me do that on a separate sheet of paper. Or you know what, I'll just do that over here. So if we wanted to find the points 0, 1, and negative 1, 2, we would substitute in our x values for c. So we would have 2 times 0, which would be 0. And here we'd have 2 times negative 1, which would be negative 2. So we can say after all of that, that the slope of the tangent lines to the graph f of x at 0, negative 1, or pardon me, 0, 1, and negative 1, 2 are 0 and negative 2 respectively. Okay. The slope at the tangent lines to the graph f of x at 0, 1, and negative 1, 2 are 0 and negative 2 respectively. Alright, moving on. Let's talk about the derivative of a function. Alright, we're pretty much already defining this. Let's formally define it though. What we can say is the derivative of f, that fancy f, at x is f prime of x. That's how we denote a derivative, is f prime of x. And we say the limit as change of x approaches 0 for our rate of change function. So f of x plus change in x minus f of x all over change in x. And then we say, provided, of course, that the limit exists. And furthermore, we can say for all x for which the limit exists, f prime of x, the derivative, is a function of x. Okay. There are some key points I'd like you to understand. First of all, that the derivative in layman's terms, is instantaneous rate of change. Instantaneous rate of change. That's essentially what we're finding, right? We're finding the slope at that single point, so we're finding instantaneous rate of change. Okay, let's talk about notation. F prime of x, that is how we talk about a derivative. We could also say dy dx, that's asking for the derivative as well. Y prime is another way. D dx of our function f of x, that's another way. D sub x of y. These are all just ways that you could see a derivative asked for. Let's see. Lastly, let's talk about what dy dx means in words. We say this is the derivative of y with respect to x. And understanding that notation will become more important as we use these derivatives for real-world applications. Let's talk about using the limit process, though, to find derivatives. And we sort of already did this with our slope, but let's do it once again on a separate sheet of paper. So, we're going to find the derivative. Can you see what I'm writing? Okay. Find the derivative of f of x equals x cubed plus 2x. Here's how we can start it off. With our notation, f prime of x equals the limit as change in x approaches 0 of our classic rate of change function, f of x plus change of x minus f of x all over change of x. And remember, we're substituting in this piece, x plus change of x, for all of our x's in our function. So we're saying change of x approaches 0, and now we're taking this piece and replacing it with every x we see. So we're going to have x plus change of x cubed plus 2 times x plus change of x minus just regular f of x, which is this. So minus x cubed plus 2x. And we put that all over change of x. That is a lot of writing. That's okay. To expand out that cubic factor right there, what we're going to do is use our, again, polynomial cheat sheet to understand how to expand that out. We would have our x cubed plus our 3x squared change of x plus 3x times change of x squared plus change of x cubed. And now we distribute out this 2, so we get plus 2x plus 2 times change of x. And then we distribute out this negative, and we get minus x cubed minus 2x. And we have that all over change of x. And as we start to rewrite things here, we're going to cancel where we can. So we've got a negative x cubed and a positive x cubed. We have a positive 2x and a negative 2x. And let's see here, it does appear that that would be everything we can cancel. So we're going to rewrite 3x squared change of x plus 3x times change of x squared plus change of x cubed plus 2 times change of x all over change of x. And what we can essentially do at this point is factor out a change of x, because everything has a change of x. So we can take that out on top, and we're left inside with 3x squared plus 3x times change of x plus change of x squared plus 2. And then on the bottom we still have change of x. Now we are ready to cancel those out. And we are left with the limit as change of x approaches 0 for 3x squared plus 3x times change of x plus change of x squared plus 2. And now we can directly substitute in our 0. So once we take this limit, we can see that we are left with 3x squared plus 2. Again, because this would become 0 and this would become 0. Oh, there we go. Now you can see it. And now that is our derivative, and that is where we stop. So we say f prime of x equals 3x squared plus 2. Alrighty, now let's move on to another example. Let's use this to find some information. So, say we are given the example, find f prime of x, find the derivative for the function f of x equals radical x, and then we want to find the slopes of the graph of fancy f at the points 1, 1, and 4, 2. And then we're going to discuss the behavior of our function of f at 0, 0. Okay, so essentially we're going to find another derivative using the algebra like we just did, and then we're going to use that derivative to find the slope at 2 points. So we're going to begin by saying f prime of x equals the limit as the change of x approaches 0 of our function filled in. So remember, for every x that we saw, we're going to instead use x plus change of x for the first one. So we're going to have radical x plus change of x, and then we have minus regular f of x all over change of x. So we get the limit as change of x approaches 0, and we're left with our original thing, x plus change of x. But as you can see, if we were to substitute in 0 directly, we wouldn't be able to just yet. We'd still get undefined. So what we need to do is some work, and we're going to multiply by the conjugate. Top and bottom. And when we do that, what we are left with is our a minus b, a plus b, so we have a squared minus b squared, which means we have the radicals lifted off both of these on top, so we have x plus change of x minus x all over change of x outside this whole thing. So x plus change of x plus radical x. Okay. Now, as you probably saw, if we have a negative x and a positive x, we get to cancel those out, and we are left with change of x approaches 0, And we also see that we have change of x over change of x, which would be okay to cross out and make just a 1 on top. So we are left with 1 over radical x plus change of x plus radical x. And now when we substitute in our 0, what we can see is that we get this to go away, and we get radical x plus radical x on the bottom, or 2 radical x's. Now we're going to use this to find our slopes at those points, so we can say m at the point 1, 1 is represented by substituting in a 1 for our x, which would get us 1/2. The slope at the next point at 4, 2, again we substitute in our 2, or pardon me, our 4, that's our x value, our 4 for x, and we would get 1 over 4. But now let's discuss the point 0, 0, because when we substitute in 0, 0, we get 1 over 0, which we know we can't have. Let's think about what this represents, though. This is an undefined fraction, true, but remember, we just found an undefined slope. So, undefined slope only happens when we have a vertical line. So in this case, what we have is a vertical tangent line to the graph at 0, 0, right? Tangent line. The tangent slope at that exact point, 0, 0, would be a perfectly vertical line. Okay. So, let's graph what that looks like, actually. Let's really investigate that. Let's make sure we're right. If we type in our y equals square root of x, we do second radical, and then we do x, and we graph it. Oh, I can see right away my scale is off, so we're going to press zoom 6. There we go, that looks a little bit prettier. And if I zoom all the way in, I can see what's happening. Now remember, this is only including my positive value, so let's make sure my table is representing what I need it to represent. Oops. Let's do table set. Let's start at 0. Let's change by like 1s because we're not taking a limit, we're just looking. There we go. Alright, so it looks as though when we substitute in, oh my goodness, I did the wrong graph. Let's make sure we do the right one. That wasn't our function. Our function was 1 over 2 outside radical x. I was missing a lot there. My bad. Now when we graph this, we can see a lot more clearly what's happening. Let's do Z6 again. Oh, maybe let's zoom in. Yeah, that was a little bit better, wasn't it? Okay. When we look at our graph, we can see that it is going straight up when x equals 0, and we know that that means it has a vertical line and the slope is undefined. That's what that looks like. Okay, so moving on from that, what we want to talk about next is using a derivative to find the slope of the tangent line. Here's the thing. What we're going to do is we're going to cut this video short because it's already going pretty long, and we're going to make this into 2 parts. So we'll call this part A, and we'll discuss part B tomorrow. All right, thanks for watching.